Welcome to the fascinating world of quantum mechanics, where the rules of classical physics no longer apply, and the behavior of particles becomes truly mind-boggling. In this realm, particles can exist in multiple states simultaneously, a concept known as superposition. This means that a particle can be in two places at once, or spinning both clockwise and counterclockwise simultaneously. It's a concept that challenges our everyday understanding of the physical world. One of the most intriguing aspects of quantum mechanics is entanglement, where particles become connected in such a way that the state of one particle instantly influences the state of another, no matter the distance between them. This phenomenon has been famously referred to as spooky action at a distance by Albert Einstein. Quantum mechanics has also found its way into our everyday lives through technologies like MRI machines, lasers, and transistors. In fact, without quantum mechanics, many of the technologies we rely on today would not exist. The field of quantum mechanics is not just limited to technology. It also has profound implications for fields like cryptography and computing. Quantum computers have the potential to revolutionize the way we process information, solving complex problems at speeds unimaginable with classical computers. As of 2021, the largest quantum computer had 65 qubits, the basic unit of quantum information. However, researchers are constantly working to increase this number to achieve more powerful quantum computers. Quantum mechanics is not just a scientific theory. It has also captured the imagination of popular culture, appearing in movies, books, and even art. Its mysterious and counterintuitive nature continues to inspire curiosity and wonder in people around the world. Quantum mechanics is built upon several fundamental concepts that shape our understanding of the quantum world. One of these key concepts is wave-particle duality, which suggests that particles like electrons and photons can exhibit both wave-like and particle-like behavior depending on the experiment. This duality was famously demonstrated in the double-slit experiment, where particles behaved as waves when not observed, but as particles when observed. Another fundamental concept is the uncertainty principle, formulated by Werner Heisenberg, which states that it is impossible to simultaneously know the exact position and momentum of a particle. This principle fundamentally challenges the deterministic nature of classical physics. Quantum mechanics also introduces the concept of quantization, where certain properties like energy levels are restricted to discrete, quantized values. For example, electrons in an atom can only occupy specific energy levels, giving rise to the unique spectral lines observed in atomic emission spectra. The concept of quantum entanglement, where particles become interconnected regardless of distance, is another fundamental aspect of quantum mechanics. This phenomenon has been experimentally verified and has led to the development of technologies like quantum teleportation and quantum cryptography. In terms of interesting numbers, a notable figure in quantum mechanics is the Planck constant, denoted by h, which has a value of approximately 6.626 times 10 to the power of negative 34 joule seconds. This constant plays a crucial role in determining the scale of quantum effects in the universe. Another intriguing number is Avogadro's number, which represents the number of particles in 1 mole of a substance and is approximately 6.022 times 10 to the power of 23. This large number highlights the microscopic scale at which quantum phenomena operate. Quantum mechanics also introduces the concept of quantum states, which describe the possible configurations a quantum system can have. These states are represented by wave functions, mathematical functions that encode the probability amplitudes of different outcomes. The concept of superposition, where a quantum system can exist in multiple states simultaneously, is a fundamental aspect of quantum states. This property forms the basis of quantum computing, where quantum bits or qubits can represent multiple values at once, enabling parallel computation. Overall, these fundamental concepts of quantum mechanics provide a rich framework for understanding the behavior of particles at the quantum level and have paved the way for groundbreaking technological advancements in various fields. Quantum superposition is a fascinating concept in quantum mechanics, where a particle can exist in multiple states simultaneously. This means that a particle can be in two or more positions, velocities, or spins at the same time, until it is measured and collapses into a single state. One of the most famous demonstrations of superposition is the Schrödinger's cat thought experiment, where a cat inside a box is considered both alive and dead until the box is opened. This illustrates the bizarre nature of quantum superposition and its implications for the behavior of particles. Entanglement, on the other hand, is a phenomenon where particles become interconnected in such a way that the state of one particle is instantly correlated with the state of another, regardless of the distance between them. This spooky action at a distance, as Einstein called it, has been experimentally verified and is a key feature of quantum mechanics. Interesting numbers in the realm of quantum superposition and entanglement include the record-breaking entanglement distance achieved in a 2020 experiment, where entanglement was maintained between two particles separated by a distance of over 1,200 kilometers. This remarkable feat showcases the long-range potential of quantum entanglement for future technologies like quantum communication networks. Another intriguing number is the superposition time achieved in laboratory experiments, which can reach femtosecond, 10 to the power of -15 seconds timescales, allowing researchers to observe and manipulate particles in superposition states with unprecedented precision. Quantum superposition and entanglement are not just theoretical curiosities. They have practical applications in quantum computing, where qubits can leverage superposition and entanglement to perform complex calculations exponentially faster than classical computers. These quantum phenomena are at the heart of the quantum revolution, promising a new era of technological innovation and scientific discovery. Quantum mechanics may seem like a realm reserved for physicists and researchers, but its impact can be felt in our everyday lives in surprising ways. For example, the technology behind magnetic resonance imaging, MRI machines, is based on the principles of quantum mechanics. By manipulating the spin of atomic nuclei in a magnetic field, MRI machines can create detailed images of the inside of our bodies, helping doctors diagnose and treat various medical conditions. Another application of quantum mechanics in everyday life is the use of lasers. Lasers work by stimulating atoms to emit photons of light in a coherent beam, a process that relies on the quantum nature of atomic transitions. From barcode scanners to DVD players, lasers have become indispensable in modern technology. Interesting numbers in the realm of quantum mechanics in everyday life include the fact that over 30 million MRI scans are performed in the United States alone each year, highlighting the widespread use of this technology in healthcare. Additionally, the global market for lasers is projected to reach over $14 billion by 2025, driven by applications in industries like telecommunications, manufacturing, and healthcare. Quantum mechanics also plays a crucial role in the development of semiconductor devices like transistors, which are the building blocks of modern electronics. The miniaturization of transistors, driven by advances in quantum mechanics, has enabled the creation of powerful computers, smartphones, and other electronic devices that have become essential in our daily lives. Whether we realize it or not, quantum mechanics is all around us, shaping the technology we use and the world we live in. Quantum mechanics has revolutionized technology in ways that were once thought impossible. One of the most exciting applications of quantum mechanics in technology is quantum computing. Quantum computers leverage the principles of superposition and entanglement to perform calculations at speeds exponentially faster than classical computers. For example, a quantum computer with just 50 qubits could theoretically outperform the most powerful supercomputers in existence today. This potential for quantum supremacy has sparked a race among tech giants like Google, IBM, and Microsoft to develop practical quantum computers. Another fascinating application of quantum mechanics in technology is quantum cryptography. By harnessing the principles of quantum superposition and entanglement, quantum cryptography offers unparalleled security for transmitting sensitive information. Quantum key distribution, a form of quantum cryptography, uses entangled particles to create unbreakable encryption keys, ensuring that data remains secure even against the most sophisticated cyber attacks. In the field of quantum communication, Quantum entanglement enables the creation of quantum networks that can transmit information with unprecedented levels of security and efficiency. The global market for quantum cryptography is projected to reach over $500 million by 2025, driven by the increasing demand for secure communication technologies. Quantum mechanics also plays a crucial role in the development of quantum sensors. Quantum sensors, such as atomic clocks and quantum magnetometers, leverage the sensitivity of quantum systems to measure physical quantities with unparalleled precision. For example, atomic clocks based on the quantum properties of cesium or rubidium atoms are used in GPS satellites to provide accurate timing information for navigation systems. Quantum magnetometers, which exploit the quantum behavior of atomic spins, are used in a wide range of applications, from mineral exploration to medical imaging. The global market for quantum sensors is expected to grow to over $400 million by 2025, driven by advancements in quantum technology and increasing demand for high-precision sensing devices. These examples illustrate the transformative impact of quantum mechanics on technology, paving the way for a future where quantum technologies will revolutionize industries and reshape the way we interact with the world. Quantum computing is poised to revolutionize the field of cryptography by offering unprecedented levels of security through the principles of quantum mechanics. One of the most intriguing aspects of quantum cryptography is quantum key distribution, QKD, which uses quantum properties to create encryption keys that are inherently secure. Unlike classical encryption methods, which can be vulnerable to hacking with advances in computing power, QKD provides a level of security that is guaranteed by the laws of quantum mechanics. This has led to the development of quantum-resistant algorithms that can withstand attacks from quantum computers, ensuring the long-term security of sensitive data. In fact, the global market for quantum-resistant cryptography is projected to reach over $1 billion by 2025, driven by the increasing threat of quantum attacks on traditional encryption systems. Quantum computing, with its ability to process vast amounts of data in parallel, also has the potential to break traditional cryptographic algorithms that rely on the difficulty of factoring large numbers. For example, Shor's algorithm, developed by mathematician Peter Shor, demonstrates how a quantum computer could efficiently factor large numbers, rendering widely used encryption methods like RSA vulnerable. This has spurred efforts to develop post-quantum cryptographic algorithms that can resist attacks from quantum computers. The race to achieve quantum supremacy in computing has seen significant milestones, such as Google's quantum computer achieving quantum supremacy in 2019 by performing a calculation in just 200 seconds that would take the world's fastest supercomputer 10,000 years. This breakthrough highlighted the immense computational power of quantum computers and their potential to solve complex problems at speeds unimaginable with classical computers. The quantum computing market is expected to grow to over $65 billion by 2030, driven by advancements in quantum hardware and software. Quantum computing and cryptography are at the forefront of technological innovation, offering solutions to some of the most pressing challenges in data security and computational complexity. One of the key challenges in quantum mechanics is the issue of decoherence, where quantum systems lose their coherence and become susceptible to external influences, leading to errors in quantum computations. Researchers are actively working on developing error correction techniques to mitigate the effects of decoherence and improve the reliability of quantum computers. Another challenge is the scalability of quantum systems, as increasing the number of qubits in a quantum computer also increases the complexity of controlling and maintaining coherence among the qubits. Overcoming this scalability challenge is crucial for realizing the full potential of quantum computing in solving real-world problems. In terms of interesting numbers, the global investment in quantum technology research and development is projected to reach over $10 billion by 2025, reflecting the growing interest and investment in quantum technologies worldwide. Additionally, the number of qubits in the largest quantum computers is expected to continue to grow, with companies like IBM and Google aiming to achieve quantum supremacy with machines exceeding 1,000 qubits in the near future. The field of quantum information science is also expanding rapidly, with the number of research papers on quantum computing and quantum cryptography doubling every few years. This exponential growth underscores the increasing importance of quantum mechanics in shaping the future of technology and scientific discovery. Quantum mechanics has captured the imagination of popular culture, making its way into movies, TV shows, books, and even music. One iconic example is the movie The Matrix, where the concept of a simulated reality draws inspiration from the idea of a quantum reality where nothing is as it seems. In the realm of literature, authors like Philip K. Dick and Isaac Asimov have explored themes of quantum uncertainty and parallel universes in their works, challenging readers to ponder the mysteries of the quantum world. Quantum mechanics has also influenced the world of music, with artists like Pink Floyd incorporating quantum themes into their lyrics and album artwork. Interestingly, the number of science fiction movies featuring quantum concepts has been steadily increasing, with over 50 films released in the past decade alone. This trend reflects the growing fascination with quantum mechanics and its potential to inspire creative storytelling in popular culture. The impact of quantum mechanics in popular culture extends beyond entertainment, influencing fashion, art, and even social media trends. For example, quantum-inspired fashion designs have graced runways, showcasing the fusion of science and style. In the digital realm, quantum-inspired art installations have captivated audiences with their interactive and immersive experiences. The intersection of quantum mechanics and popular culture continues to evolve, shaping the way we perceive and engage with the quantum world. Quantum mechanics continues to push the boundaries of our understanding, with exciting developments on the horizon. The global market for quantum technologies is projected to reach over $1.3 trillion by 2027, reflecting the immense potential of quantum applications. In the field of quantum computing, researchers are working towards achieving quantum supremacy with machines exceeding 1,000 qubits. The exponential growth of research papers on quantum information science underscores the increasing importance of quantum mechanics in shaping the future of technology. Quantum-inspired fashion designs have been showcased on runways, blending science and style in innovative ways. With over 50 science fiction movies featuring quantum concepts released in the past decade, it's clear that quantum mechanics has firmly established itself as a source of inspiration in popular culture. The number of qubits in the largest quantum computers is expected to continue growing, with companies aiming to achieve quantum supremacy with machines exceeding 1,000 qubits. Over 50 science fiction movies featuring quantum concepts have been released in the past decade, reflecting the increasing fascination with quantum mechanics in popular culture. The global market for quantum technologies is projected to reach over $1.3 trillion by 2027, highlighting the immense potential of quantum applications.